Now, okay, welcome everybody back. This is our third Optimization Oslo seminar. We're very happy to have Coralia Cartis from the University of Oxford, who's going to speak about sparse random embeddings and their applications to optimization. So, Coralia, the floor is yours.
Thank you very much. Thank you very much, Thomas, for this very nice opportunity. And I am very sorry not to be there in person. But I am grateful to these technologies that allow us to still talk to each other and hope to visit in the near future. So today I will talk about a few pieces of work and I will try to put them together under the same umbrella of essentially how to do efficient sketching and how to apply that to various classes of optimization problems. And some of this work is with my PhD student, Zhen Shao, and collaborator Yari Fox at Rutherford Appleton Laboratory. Also our collaborator at Numerical Algorithms Group, Jan Fiala. And some of the work towards the end is with my former PhD student and still collaborator, Lyndon Roberts. So let me begin. Okay. So again, I want to talk about how about sketching and some results we have on sketching, which is a tool from numerical linear algebra, from randomized numerical linear algebra, and then in particular about how to do sketching with sparse matrices and how to get good dimensionality reduction with them. Then I will apply these sketching ideas to improving solvers for linearly squares, and here it's a certain approach. I will describe it. It's to use sketching for preconditioning, and then I will talk about how to use sketching for improving nonlinear optimization solvers in their scalability properties. And I hope to talk about both the derivative-based case, when we have at least some parts of the derivatives, and for derivative-free case. So let us begin our journey. So sketching, what is sketching? So can you see my screen? Well, just my whole screen. Can you see my whole screen?
Yeah, we can see the screen and the mouse.
Okay, so and I don't need to minimize my viewing windows or anything. You can see
no.
Great. I think that's just my view on the computer. Okay, great. Right. So given so sketching essentially relies on this Johnson-Lindenstrauss lemma, and this tells us that if I have a given vector x in Rn, and n throughout this talk will be considered as a large dimension. Okay, so n is large, x is given. I want to project it from the high dimension Rn to a smaller dimensional space in Rm. So m is small by comparison to n. Can I do that? I can do that if S is a scaled Gaussian matrix. And how do I want to project it? What properties do I want to preserve? I essentially want to preserve its length. So Gaussian matrices act as random projectors that preserve length of the vectors they project. And here's the full result, the full statement. So if S is a Gaussian matrix and the small dimension here M is of this form where delta S is the probability of the success that I successfully preserve the length essentially, and epsilon S is the accuracy to which I managed to preserve it. Okay. Then indeed I can get my embedding, so-called embedding properties that are length preserving. This is a high probability result because this delta appears as a log in the size of M, so I could replace it there with a value, and then here I would get an exponentially high probability of success of this embedding. So with exponentially high probability, I can preserve the length. How should I understand this result? Well, if X was a random vector, I have in this plot this relative error here. So the relative size of the projected vector with a Gaussian matrix. And what you can see is that this relative length concentrates around 1. So indeed, this is a concentration of measure phenomena. But what happens if X is not random? If X is not random, then I can think of S as acting both as a transformation and as a sampler. In other words, it's a random projector. So it randomizes it, and then it looks just like this picture once we've randomized the vector X. The main thing in this result that I want you to note is that there is no ambient dimension dependence in M or in epsilon S. There is no N dependence. In other words, I can project from high dimensions to small dimensions, and I can preserve length, and N does not come in. What if I have not just a vector, but finitely many vectors? It's very similar. The result is very similar. But if I want to go to infinitely many vectors, like a subspace, if I want to correctly project a linear subspace, in particular, if I have a given matrix A that is n times D, and I want to project correctly the range of A, the column space of A, then I can do so, but the dimension of the subspace comes in. In particular, M is proportional now to D, which is, say if A is full rank, then it's D here. If A is rank R, then here instead of D, we have R. So you can project with scale Gaussian matrices, you can project as much as the dimension of the subspace. In these plots here, I showed that this result is essentially tight, because just numerically you can see that if again you look at the relative error of the length of the projected vectors in the column space, and against, so on the horizontal axis I have M over D. So you can see that this residual is large when M is less than D. So I cannot project correctly if M is not proportional to D. But as soon as it is, you know, it's 1 point very small number, this projection actually works. And these plots apply to different randomly chosen matrices A, structured or Gaussian or sparse. Okay, the downside of all these results is that though N does not appear in the size of S, in the small size of S, okay, or in epsilon S, it does appear when you form S times A, because S is a dense matrix. So for that reason, and maybe others, we want to think about sparse sketching matrices. The simplest sparse random projector is a sampling matrix. So if S has one non-zero per row, then when I apply S to A, all I'm doing is I'm uniformly at random sampling rows of A. As you may know, this, and as it's rather obvious, this is not a good embedding matrix. So sampling does not have good embedding properties, because when I do that, if A has an important row that's of substantially different magnitude than the rest of the rows, and if I miss it when I do my uniform sampling, then I won't be able to project correctly. Indeed, sampling can only be shown to have these length preserving properties, these JL or subspace embedding properties, when under some assumptions on A, and we call that if A has low coherence. This coherence notion, just for your information, looks at looks at the SVD of A, and then it takes the norm of the rows of U, and takes the largest the largest norm of the rows of U. That's the coherence notion, and it measures essentially this idea of having similarly important rows in magnitude. If that's the case, so if these rows, if the rows of A are similarly important in magnitude, then the random sampling matrix can be a JL having JL embedding properties and subspace embedding properties. But what you notice here in the size of M is that the coherence of A comes into the size of M, and also the log D. Okay, so the Gaussian matrix is viewed very much as the optimal sketching matrix because of this proportionality between M and D. So you can reduce the dimension of the subspace with Gaussian matrices as much as possible. But once you move away from Gaussians, then sampling matrices have this, the size of M deteriorates. Are there better sparse random ensembles? Yes. So hashing matrices have non-zero per column. So not per row, but per column, plus minus ones, let's say. And so we do one per column instead of one per row. And when you apply such an S matrix to A, then you will touch the rows of A. You will start forming sums or differences of rows of A. And this, numerically, people have noticed that hashing, or count sketch as it's called, has almost as good as properties, embedding properties, as Gaussian matrices. But theoretically, this was not, people couldn't really prove that. So the results for hashing matrices, if M is D squared, so for a general matrix A, if M is a multiple of D squared, then we can have a subspace embedding property. But that's much worse than D. So what about if A has low coherence? Well, Bourgain and others prove that if A has low coherence, then you can get a smaller M size here. So the size of the sketching, the size of how much you can reduce the dimension of from your ambient space to your projection space, M is now proportional to D log square D. And you can see that the coherence does not appear in M. What we were able to show is that if you further restrict the class of matrices A in terms of their coherence, then you can get here M to be proportional to D. So you can recover here the optimal dimension dependence in terms of the size of the projection space. So we were pleased with that. I don't think this result is tight in terms of the coherence. So the coherence is less than 1 over D. We think this could be further improved. So maybe the class is a bit larger than that, but that's what we were able to show. Now, these are matrices that have one non-zero per column. What if I have more than one non-zero per column? If I have more than one non-zero, we can call that S hashing. Then you can enlarge the class of matrices for which you can project correctly. So M is still proportional to D for S hashing matrices, but you can slightly enlarge the class of matrices. The coherence you can allow for larger coherence, slightly larger coherence of the matrices that are embedded correctly. Okay, so these are some of our results. I can say a bit more, but I don't want to maybe say too much. This result for matrices that have more non-zero per column, in this result, we were able actually to prove something more general. We have a way of going from any embedding property for one hashing matrices to embedding properties for S hashing matrices. So we can say that if you have a you can have a result, you have a result that gives an embedding property for one hashing matrices, then we can immediately tell you that your result extends to S hashing matrices for this larger class of matrices scaled by square root of S in their coherence, and you can obtain the same result. And essentially, our result relies on going from the case where you have S with, say, 3 non-zeros per column. You can think of applying that to the U vector in U matrix in the SVD of A as having another U matrix where you just repeat the matrix U with appropriate scaling. So we can we can find a distribution. We can say that in distribution, this applying S to the original U matrix of your matrix A is the same as constructing this artificial U that repeats the matrix U 3 times and acting on it with one hashing matrix. So using this idea, we were able to show this more general result for S hashing. Another improvement we've done is that you can go from, you saw that when I talked about, say, one hashing matrices or S hashing matrices, I talked about applying them to matrices with low coherence. Now, you can change the setup a little bit, and you can say, well, I'm going to just have any A, okay, provided n is at least d to power 3. So A is significantly overdetermined. So provided A is sufficiently overdetermined, then I can have a coherence reducing transformation. So there are several matrices that are in this class of coherence reducing transformations, Hadamard transforms, Hart transforms, and so they take randomized rows. Typically, they are subsampled Hadamard transforms, and so you take subsampled Hadamard transforms by randomly selecting rows, and you can show that these matrices, they are much better than just the sampling matrix, because the Hadamard transform takes care of the coherence properties. What we have proposed is to replace in the literature all this subsampling of Hadamard transforms or other transforms with hashing them. So if you do hashed Hadamard or similar coherence reduction transformations, then we can get there the size of the projection to be proportional to D. So this is a very, if I may say so, important result, because with subsampling here, you still can't get M proportional to D. And furthermore, we can actually see numerically that these work much better than subsample Hadamard transforms.
Is HD one matrix, or is that the product of two matrices?
It is the product of two matrices. Sorry, there is a diagonal scaling that comes in. Yeah, it's just the usual way people do. We just took from the literature. Yeah. It's like diagonal plus minus ones. So we just took exactly what people use in the literature for these coherence reducing transformations. We tried 2 or 3 of them, and so they do this HD as well. So we just took what they are doing, but we just replaced the sampling. So they do a sampling matrix instead of SH. Our SH is a hashing. Yeah. And in the literature, people do subsampling. Okay. And so we just did that change. And encouraged by these results, and what we found is in this plot here. So in a moment I can explain to you a little bit more like what is in this plot. In this plot, I will tell you how we constructed it. Essentially we used sketching for preconditioning a given matrix A. So the preconditioner R here is constructed using this sketching. And what we found is that the condition number is much better in blue, and in red is the subsampled variant. So if we use a subsampled variant, then we have it's a much worse preconditioner. But when you use ours, it's really good. And you want it to be in this regime here, because this is on the horizontal axis, this is M over D. So you do want M, M is the size of the projection, the size of S. You do want M to be as close to 1 as close to D as possible. And so you do want to be here, and exactly in this regime, ours is much better than what the literature gives you. Okay. So we played around with these things. I'm not claiming I'm not a randomized numerical linear algebra person, but I was absolutely fascinated with these techniques. And with my students and Shao, we spent time thinking about them. And then after that we thought, okay, so now we've learned a bit more about sparse embeddings. So let's see what we can do with them for optimization. So the first thing we did is we looked at the gold standard of randomized numerical linear algebra, which is Blendenpik. So Blendenpik is an algorithm for least squares, linear least squares. So first, let me just start by saying, okay, what is the most naive way you could apply sketching to solving linear least squares? And that's not Blendenpik. Okay, Blendenpik is a bit more, and you may be familiar with it. It's a bit more, it's a different kind of idea. So if I take this linear least square, so A is still n times d. Okay, A is n times d. And I could say, well, so A is overdetermined. So let me just sketch A. And that means that immediately I reduce in here the size of my least squares in the number of observations that number of terms I have, number of observations I have, number of data points, and I could solve these reduced least squares. And, you know, I can have some savings, especially if S is sparse. And if S is a subspace embedding, then when you solve for your YS here, in the residual, you are close, you are a multiple of the original residuals. These are just consequences of the embedding properties. So if this is a linear least squares that has a zero residual solution, so this right-hand side here is 0, then you can do this with reasonable accuracy. But if that's not the case, then you won't get accurate solutions with this S times A. You won't be able to get your residual within, you know, your desired accuracy. So there really is an issue with the accuracy to which you will be able to solve your problem. So people have tried something else with sketching for linear least squares, namely this Blendenpik idea. So don't sketch, okay? So don't sketch there. Sketch your A for preconditioning only. So draw a matrix S just once, a sketching matrix, apply it to A, and then compute some factorization for it. For example, you can do SVD, but it's expensive, so let's do a QR. So that's the original Blendenpik. Do QR, and then use R to precondition. Okay, so then you end up having still, so what you've reduced here is you've reduced not your observational space like in the original simple sketching. You've now reduced your variable dimension, Y. So now you're solving for W, but A is still A. So essentially, you've just used sketching for preconditioning, and you're still essentially solving pretty much your original problem. So in this way, you can get essentially, you know, very accurate solutions, irrespective of your type of least squares. And this really works. This works well. So the original Blendenpik, in the original Blendenpik, S was Gaussian matrix. They were doing QR. Then LSRN proposed to use S to be a sparse Gaussian matrix. And instead of QR, they are doing SVD for reasons of rank, because in this original Blendenpik framework, they couldn't deal with rank deficient least squares. And also LSRN tried to parallelize and so on. We didn't deal with any parallelization issues.
So is the idea that SA is so small that the matrix factorization doesn't cost that much? Because I mean,
yes. Thank you, Thomas. Yes, I did not, you know, emphasizing by omission. I didn't mention the key point there. Yes. Thank you. So the saving is not just that here you solve in the least squares in the reduced space, but also that when you factorize S times A, S times A is essentially D times D, pretty much D times D. just D is the small dimension, right? N is the large dimension. N is very A is overdetermined. N is large. So you're thinking that, you know, this S times A is just a bit larger than D.
Right. Okay.
Yeah. Yeah. Exactly. Yeah. So we thought, okay, let's try to improve these things. First of all, I want to do like some other kind of like really sparse sketching. And I also want to deal with input that's sparse. So what if A is sparse? None of these solvers exploited sparsity of A. Blendenpik certainly doesn't. LSRN, I can't exactly remember, but it's nothing very explicit. So we just thought, okay, let's just try, you know, we know some good numerical linear algebra papers like iterative solvers for, sorry. Okay, one more thing. Sorry, so in here, so what do you do with these linearly squares here once you preconditioned it? Well, you precondition it so that you can do an iterative solver. So people do, you know, LSQR, LSMR, something like this on this LSQR, in fact, originally on this solver here, on this reduced linearly squares. Okay, so then we thought, okay, let me just see what we can do here. So we have a solver called Skills. It's available on GitHub, and it can do it treats the input A depending on whether it's sparse or not. So if you tell the solver that it is dense, then it will go down one route of solution. If that A is dense, it will go down one route. If it's sparse, another alternative. So if A is dense, then instead of doing you know, subsample randomized Hadamard as in Blendenpik, we do this hashed version. We also wanted to do to deal with rank deficient A, but not do SVD because that's too expensive. So we try to do column pivoted QR, but that is very expensive as well. So we then found out that Gunnar Martinsen, who's like one of the core people in randomized NLA, has a randomized column pivoted QR solver. So we are applying that. So it can deal with rank deficient input. Then for sparse problems, so if A is sparse, we apply hashing matrices with typically 2 non-zeros per column. And for the factorization, we do sparse QR. So we do Tim Davies' SPQR solver. And then we do LSQR on the reduced system. But in fact, you know, I have students who have tried LSMR, and LSMR works even better than LSQR, but we haven't yet implemented that in Skills. So so then we tried the solver, and here's our numerics. On the left-hand side, we have sparse random problems. We compare. So I'm only showing you our results for sparse problems. We have actually also improved on Blendenpik. So our dense solver, the dense part of Skills improves on Blendenpik and LSRN. The improvements are maybe not as dramatic as in the sparse cases for these algorithms, but still we get improvements over Blendenpik. Okay, so for sparse problems, we have if the matrix A is a random problem, sparse, we have different ensembles: coherent, incoherent, semi-coherent, and we run so these are time plots and on different sizes, and we compared with LSRN, which is in purple, SPQR in yellow, which is just the factorization based with sparse QR for direct solve for linearly squares. We also compared in blue with HSL. So HSL is an iterative solver that Jennifer Scott and Nick Gould have put together. That is really the algorithm to beat for iterative solvers for linearly squares. And for sparse linearly squares, I mean, it's really very good. So that our aim was to try to beat that. So it's a deterministic solver. So in red is our code, and you can see that we are doing very well on sparse ensembles. On random A. Now, what if we take the sparse Florida collection, all right, which are its structure sparsity? So this is quite something to be concerned about, because random sparsity is quite different structure sparsity. And in fact, often, a random sparse matrix may destroy these nice structures. So what we found there, so these are now performance plots on time, but performance plots. So the higher the curve, the better. And so we are showing the number of problems solved, each curve, so the number of problems solved from the collection that the solver solved, that for which the solver was within a fraction of the best solver. So you can see that in blue is the RAL HSL code. And so the higher the curve, the better. So in blue is the code. And these are very over-determined least squares. So n is greater than 30 times d. So then we beat this code, okay? But in other cases, so if we don't have such over-determined problems, then the HSL code beats us. We also beat HSL when we have very ill-conditioned problems. Okay, so when we have ill conditioning, we also have a pretty robust approach, or when the sparsity is not that large. So what the HSL code does is an incomplete Cholesky preconditioning for I think LSQR or something like that. And that solver that is hard to beat because it depends on the number of non-zeros that you have rather than the dimension of the problem. And this is why if the codes depend quite a bit on the dimension of the problem, then we can beat them. But if you depend on a number of non-zeros, then the sketching may not be so may not give you it won't profoundly disadvantage you, but it won't give you like the best results.
Just out of curiosity, what happens if n equals d? I know the theory says you won't have this relation m equals big O of d times log and so on. But like, have you tried it where like n equals d, so where A is a square matrix?
So, if A is the square matrix, you're really not going to see much gains. I mean, will it improve your conditioning somehow? Maybe. I don't know. Yeah, but I would say I'm only interested in these techniques as a tool to do dimensionality reduction.
Yeah.
So I think of D as not necessarily big, but
Now,
in fact, yeah. But it's a valid question to ask. So will it improve anything? Or how bad will it be,
Yeah.
Yeah.
I'm thinking if A is like a Hessian, if A is like a Hessian of a C2 function, right? Then n would be equal to D, right? But,
yeah. So then so if you so we will see. I can say a bit that at the end, because of course when we apply this to optimization, we are very much in that case, and then these techniques will apply, for example, if the Hessian is low rank.
Okay.
Yeah. So that would be kind of how I would think about it. I would do it for D times D, but if it's low rank.
Okay.
Yeah. Okay, this is the correct answer. Good, very good question, Thomas. So the answer is that would be useful if the matrix is low rank.
Very nice. Okay.
Good. Any more questions? Because I will move on to wait a minute. Yeah, I will move on to nonlinear problems now. Okay, so right. So how can I use sketching now? So I did sketching for preconditioning. Now I want to go back to kind of just thinking, stepping back again and thinking, how can I use sketching for optimization more generally, for improving scalability properties of optimization algorithms? So if the optimization problem has many variables or many terms, how can I use these sketching ideas? And what I will say next, at least the next few slides, it's kind of very, I will try to do kind of more basic sketching and just see how I can incorporate that in my algorithms and what can I get with it. But first, let's see how sketching is actually already used quite extensively in current methods. for especially data science applications. So this is just the, you know, the main, some main possibilities here. So if I have a binary classification problem, so in problems where it's essentially in supervised learning where I have data and I'm trying to find a continuous model that fits my data, that I can then use to predict some properties on unseen data. For example, you know, in binary classification, then I'm trying to find a linear separating hyperplane that just gives me like a linear regression problem. But then I have deep neural nets where I'm trying to do a similar thing, but when my predictor model here is some it's essentially the deep neural net that I'm trying to construct, and it's just say some kind of function like sorry, I'm really
sigmoid?
Yes.
Sigmoid? Okay.
Thank you. That I'm applying to convolutions of my weight matrices and biases through the net. We are looking at minimizing some kind of loss function. So for every, and then sorry, in my last plot here, I have nonlinear regression problem. So there, my model is some kind of nonlinear least squares that again, I'm trying to fit through the data in some regression sense. So in the end, what we end up having is a sum of functions, okay, a sum of functions where I have my model coming in at the data point, and I'm trying to match it to the given data at that point, a given observation. So I have this sum of functions. There are many observations in the, there is a lot of data points in the sum, so a lot of terms Fi. And also typically the number of variables X is also large. So like in a deep neural network, right, I have to find all these weight matrix entries and biases. So X is also large. So everything is large basically, but it's a deterministic formulation with the thought that in fact underlying it, it's actually stochastic. So in it's standard for this sum of functions to do the following, to do stochastic gradient descent. And let me briefly mention how I can interpret stochastic gradient descent using sketching. Let Sk be a sampling matrix with one non-zero per row, and let F be a vector that has all these Fi entries. So the vector F is a long vector, and each entry corresponds to a data point. It's this residual at every data point. And then I can look at applying Sk to this long vector because I have many data points and summing over, say, m of them, right? So I can form this reduced objective where I sample my data points. In other words, I subsample uniformly at random terms in Fi, and then I take a gradient step, a negative gradient descent step, just say 1 on this objective, okay? And then at the next iteration, I again sample my vector of data points or residuals at the data points, and again, I take another gradient step. That's exactly stochastic gradient descent. So sketching with sampling matrices comes into stochastic gradient descent with a batch size of m. So when I take m terms at every step from this sum of functions. Similarly, I can do this for nonlinear squares or linear squares, which would amount to this basic application of sketching for, say, linear squares, where I sample in the observational domain. So I sample rows of A. And there is a vast literature on this, on how to do better here than just this uniformly at random. And typically what you get when you do this sampling matrix Sk here, you get convergence with positive probability or convergence of the algorithm in expectation with some, you know, additional bells and whistles. Now, another thing you can do is not sample in the observations, but especially sample in the variables. So what if because X, the number of entries in X is also large. So what if I just uniformly at random select entries of X and just minimize my function on those, well, that is the same as applying this sampling matrix Sk transpose, applying its adjoint to reduce vector y. So that's nothing but randomized block coordinate descent. So when I sketch with standard sketching, standard sampling, for when I in the observational domain gives me stochastic gradient descent, and in the variable domain gives me randomized block coordinate descent. And for all of these variants of algorithms, standard, very used algorithms, the convergence result is just with positive probability. So based on what I told you, Sk as the sampling matrix is just a poor embedding matrix. It just doesn't have as good properties as other matrices like Gaussian or hashing. So can we do better with other random matrix ensembles? And in particular, can we prove better convergence properties? In particular, almost sure convergence, rather than just convergence with positive probability. It's not, it's not even exponentially high probability. It's just positive probability. That's what you have classically for stochastic gradient descent variants and for randomized block coordinate descent. So here's some ideas. I know I'm soon running out of time. So let's take, from now on, I only talk about variable reduction. So I'm not going to talk about stochastic gradient descent variants. I'm only going to talk about essentially block coordinate variants. Okay, so I'm only going to try to reduce the size of x. So I go back to just minimizing a smooth function f of x, deterministic, and I look at the standard methods that solve such a problem. So and they proceed as follows. Okay, these are like gradient descent algorithms or Newton type methods. At every iterate xk of such a method, I look at my nonlinear function f, and I can view all these methods as doing the following thing: constructing a local approximation of my function f around the current xk, and then minimizing this reduced simple model, simple Taylor approximation to calculate a step. So if I want to approximate just with, so I can approximate with this kind of approximate second order here. So BK is some second order matrix that could be absent if I just have a first order approximation, or it could be present otherwise. So if BK is absent, this is the gradient descent. If BK is present, this is, and if it's like close to the second derivative of f, then this gives me just Newton type methods. So in nonlinear optimization algorithms, I solve at every iteration of the algorithm this simpler approximation to get a change Sk that I then append to my iterate xk and check if I've made progress in f or not. And if I have done, I take this step. If not, I adjust some algorithm parameter like a trust region, or I change my line search or my learning rate. I try to reduce the step so I can make some progress in f. So that's kind of just like a 1 minute overview of nonlinear optimization algorithms. Now, what I want to do in these standard methods, line search, trust region, regularization, take your pick. I'm not going to solve this full dimensional model. Okay, I'm going to solve a sketch. So I will take my Sk matrix, that's m times n, and I will apply it to S. So in other words, I will let my direction S be S chi transpose S hat, where S hat lives in Rm. So here are the sizes. So I've reversed, I've transposed my sketch. So S is always m times n, and S transpose in reverse. So we have this. So S. So now I replace my S here with this sketch direction S hat. So I get this reduced model. The model now lives in the subspace Rm, and I can see that here I have a projected gradient, and here I have my projected second derivative matrix that, again, you can ignore if you want. So I am thinking that here I will have a double gain when I have such a model. First, I calculate S hat, it's easier to calculate S hat because it's just a smaller dimensional calculation. But also that I don't assume that in my method I will have my full gradient. I just assume that I have a projected gradient. If Sk is a sampling matrix, I'm only requiring here to have some finite, say some entries in the gradient, some of the partial derivatives in the gradient. So I don't need to calculate all my finite differences for the gradient, but just a subset of them. Okay. The rest of the algorithm proceeds the same as the nonlinear, the standard nonlinear. So I'm not doing anything much different there as compared to what I just said. I check for progress. I take the step in the full space or not. Okay, so I go back into the full space with my reduced step to calculate the iterand. But I just change this inner part, and I change what I'm asking from the oracle that gives me a derivative information. I'm just asking for reduced gradient, reduced Hessian. So under these general assumptions here, that the sketch is bounded above and that the length of the gradient is preserved with positive probability, I can show almost sure convergence of my algorithm, and I can show I can also establish a global rate of convergence. This global rate of convergence is proportional to epsilon to -2, where epsilon here, not epsilon s, which is the accuracy with which I preserve the length and can be like a half. Epsilon here is the small number, and is the number is the accuracy on the length of the gradient at termination. So I don't assume that I see the gradient in the algorithm, but I can guarantee that the algorithm will find a small gradient below epsilon in order epsilon to -2 iterations. This is the complexity of the deterministic algorithm when I have full problem information available. And this complexity only changes by this constant factor here, depending on delta S, on 1 minus delta S, which is the success probability of my correct embedding of the gradient length. So under these mild assumptions, I have almost sure convergence. Now, looking at this this property here, this is just JL embedding. So if my matrix SK has JL properties for one dimension, for a subspace of dimension 1, I can get almost sure convergence. So in particular, I only have a one-dimensional subspace that I need to embed correctly. So M can be a scaled Gaussian, and SK can be a scaled Gaussian, and M here has no ambient dimension dependence. It's just the pure JL property. That's all I need. I also can have S hashing matrices, and I can get enough. If S is, I have to have more than one, then I have nothing about coherence worries here, and M can be, again, small. Epsilon S is not small. Epsilon S here, I don't care what the constant is. I just care that there is a constant there. And so I only, so this M here, so that I can reduce the dimension of my variables to a small dimensional space in which I compute my direction. If SK is a sampling matrix, though, based on what I told you earlier, this is not a good sampling matrix. So if I try to have the same result for block coordinate results, block coordinate methods, I am unable to get it unless I make assumptions on the problem. So with block coordinates, you can't have almost sure convergence for an arbitrarily small size of the block. Well, at least, in this framework, I can't prove it to you because I need an assumption on the problem. If I assume, you remember that I told you that, a sampling matrix may miss important entries. And it's true, like I see this here too. Like if I miss an important entry in the gradient with my choices of block, I will not get a good, I cannot show almost sure convergence. So I have to assume that the entries in the gradient are similarly important in magnitude. So if I assume that my problem satisfies some kind of coherence requirement for the gradient, then I can show almost sure convergence for for randomized block coordinate descent. Okay, there is a connection here between our framework and block and probabilistic models. And Thomas is aware of this. This is a more general class of models where you have these local models, like I was telling you, but not full dimensional. They are not accurate, not close to the full dimensional model at every iteration, but only with a certain probability. So we have something similar here, that our model is close to a Taylor model with a certain probability only. So our theory kind of fits in that, and quite a bit of the convergence ingredients are from the probabilistic model theory. However, our assumptions are much weaker. So these requirements here, if you look at this requirement here, this is much weaker, and you cannot really compare it with the requirements for probabilistic model in the probabilistic model algorithms. In theory, sorry, this is more like a comment for Thomas or for people familiar with this, just for 1 second. In require that your gradient component-wise is close, your approximate gradient is component-wise close to the true gradient with a certain probability, you know, and within trust region. But here you just need to preserve the length.
Okay.
Yeah, so so it's quite different and much weaker. Okay. Right, so I won't go into this too much. I can apply this to Gauss-Newton methods. So what can I get with a block method, right? If I have a nonlinear least squares problem. So this is a nonlinear least squares setup. If I apply, I can just show you very, very quickly to give you a sense. This is still, I'm doing just blocks, but I'm just showing you kind of what happens. So I'm doing iterations on the horizontal axis and objective on the vertical axis. If I use the full model at every iteration of my nonlinear method, here Gauss-Newton for nonlinear least squares, state of the art. In purple, you know, of course, I'm going to take very few iterations. And these block methods, depending on the size of the block, they take more and more iterations. But when I look at runtime, because an iteration, you know, it depends on the method. When I look at runtime, of course, my full dimensional model takes much longer than these block methods. And also, when I look at in this last plot here, cumulative block size counts how many columns of the Jacobian, how many finite differences in my gradient I calculate at every step. I'm also gaining a lot. So I don't need so much problem information. Of course, this is like I'm giving you like the best performance. Like this is quite a simple problem here. It's quite nicely behaved. But if I have, you know, you can see stagnation and low accuracy results for some of these methods. And I would say that in the derivative-based case, quite a bit more development is needed. I should stop. I will stop. We have a paper on the next bit here, which is derivative-free, and we use sketching in derivative-free in quite a different way. If I can have 1 minute. So I'm not going to. I'm going to have the same as before. I'm going to calculate a low dimensional model. But the problem in derivative-free methods, the methods that I'm worried about, model-based ones, they are very similar to what I said before, but now you don't have this, even the full dimensional model here just doesn't have the gradient at all, doesn't have the hash, and it's constructed by interpolation of function values. And the problem is that it's very expensive to calculate this interpolated model. So what we did is to say, draw a random subspace, calculate the interpolated model only in the subspace, and then calculate your step in the subspace, then find a better point, draw another random subspace, and calculate the model in the subspace. And this we can do this to get better complexity and also very good numerical performance. We are very careful with algorithm development in this case, because we are not going to abandon our local model. So we don't just draw a random subspace, construct a model, and completely abandon all the points, because we are abandoning potentially expensive evaluations at those points of our objective. So what we do is we keep quite a bit and then draw just a smaller random subspace orthogonal to the current one. And so that we always, in total, we work in a small subspace, but we also are careful with evaluations. And what we find numerically is that we make progress in DFO while other solvers time out. And you know, the full dimensional solvers have not moved at all, and we've already made some improvements. And the scalability of DFO is like a really big issue, and we've managed to make improvements on that. Thank you very much for your attention.
Great. Does anybody who's online who would like to ask a question, please write it in the chat and I'll read it off for you. Otherwise, is there anybody in the room besides me who would like to ask some questions? Okay, then I will start. Okay, so thanks very much for the rather convincing presentation. I guess I have a number of questions. So the first is maybe just for my own understanding. So that whole discussion in the beginning about the relation between N and D and so on is for optimization maybe not so relevant because D is always equal to 1, right? Because the way you used it was that the matrix A was the gradient, right?
So for linear least squares, that is relevant. For linear least squares.
Yeah.
Yes, because in the linear least squares case, you know, when I do this S times A for preconditioning, there it's relevant. Right. Yeah.
But then for the optimization stuff you did afterwards.
For the optimization stuff, no. For the optimization stuff, no. But yeah, for the optimization stuff, no. The coherence stuff is relevant though, because it distinguishes between sampling and other things, and log methods and other things. And so continuing on the optimization. I mean, so just to clarify, some you know, so the first part, right? I maybe I went into too much detail, but it's also like we worked on that, so like I felt I should explain it properly.
Yeah, no, it was fascinating. And I guess, I mean, to build on those questions, have you thought about any way of doing this for non-smooth optimization, even non-smooth convex optimization, where you just take a piece of a subgradient? I know that's a bit more difficult because partial subgradients or subgradients aren't just products of partial subgradients, but have you thought about that at all for like non-smooth objectives?
So that's a really good question. That's a really good question. No, we haven't. That's the answer. So definitely in all of this, we haven't done that.
If I think about your training example, and I have rectified linear units, right? Then I'm going to have kinks in those lower.
Yeah. No, I know. I mean, we kind of smoothed out everything and tried not to worry. So we just did like a regression there, so that it wasn't through a deep net. We didn't put it through a deep net.
But do you think it could work? Do you think the theory could be extended to non-smooth problems?
I mean, I expect so, because you know, I expect so because you know, there are also you look at subgradients. So you're looking at here, you would try to, with this framework, to capture the subgradient information somehow. So I mean, I don't, but on the other hand, you know, we go back to probabilistic models, and even that I don't know if it's been extended for non-smooth optimization.
I guess for like stochastic subgradient.
So stochastic, yes, stochastic, right. So if I just mean stochastic, then yes, but sorry, I mean, I thought it's not.
So you're saying deterministic, but with probabilistic methods. That's
so deterministic non-smooth, I'm not sure. Like I haven't seen this. Stochastic objective, it has been extended. Some, you know, there have been extensions to it. Yes, already. So not myself, but there was a paper recently that extended Storm to have sketching in the variables and stochastic objectives. But I mean, it's just what you think. It's taking this framework for the variables, and then for the objective, it's just doing what Storm is doing. Looking for accuracy within truss region size, you know. And so, but there is a paper. Yeah, there is a paper. There is a paper.
And do you think there's any hope of extending it to constrained optimization? So if I had equality nonlinear optimization, or maybe even inequality constrained nonlinear optimization.
But so
like if you take the analogy of what you were doing just now, right, where you did basically the, I guess, quasi-Newton step and then truss region with quasi-Newton. If you did that instead for maybe the subproblems in an SQP method, right?
Yeah. So no. So I think, I think one can do it, but the question is, what will I do with the constraints? Do I want to sketch my constraints as well? This is, my linearized. So I think that for the constraints case, I think that's actually quite interesting. Also, so I think that's quite interesting, because the question, so surely I can do that for the objective, but for any like merit function, right? Like in an SQP, but then I will have some linear constraints, let's say,
right?
SQP. So what do I want to do there? Do I want to, I would reduce the dimension there as well, I suppose.
Yeah, I'd rather have less variables than, also and less equations, but if the number of variables are smaller.
Yeah, it's interesting. I haven't thought about it, but I think that's actually quite interesting. But I don't expect that it would be necessarily so difficult to extend, I would think.
If you do composite step, sorry, go on.
Yeah, you have to have some like KKT, some kind of KKT sketch, right?
Right.
So interesting question. I haven't thought about it.
Because if you do like a composite step SQP type method, then you have some problems that look like your linear least squares problems, right? Where you have step-by-step feasibility optimality, and it seems like this would immediately be applicable to that.
So maybe we should talk some more.
We should talk about that.
I haven't thought about it. I haven't thought about it at all.
Okay.
So yeah.
Great. Any other questions from the room? Anybody online who would like to post a question in the chat? If not, then let's thank Cora again for the very interesting talk.
Yeah.
Wait, we forgot. I'm still recording.
I forgot. It just came out.
This will be on.
Thank you very much, and I hope I wasn't too technical, and thank you for your attention.
That was great, thank you. So I'll see you tomorrow then.
Yeah, talk tomorrow. Yeah, bye.
Bye.